Parkinson's disease is a neurodegenerative disorder that affects movement control, characterized by a slowness of movement, muscle rigidity, and rest tremors. More than 10 million people worldwide are living with the disease, which there is no cure for. These symptoms make various daily and leisurely activities significantly more difficult, particularly those which require fine motor control.
We chose to focus on designing an innovative solution to enhance the ability of Parkinson's disease patients to play board games, and notably chess. Our board game controller is designed to offer users a more interactive and engaging way to play chess, while specifically addressing their motor control challenges. The output of this device is the movement of a robotic arm through the use of an EMG signal that indicates when forearm contractions occur, as well as an array of 4 ultrasonic sensors which are controlled by movements of the user's arms when it comes within a threshold proximity of the sensors.
The broad arm movements that the ultrasonic sensor array requires are a more user-friendly way for those living with Parkinson's to move chess pieces around a board, rather than the regular small and controlled movements that chess and other games involve. It also serves as a means of practicing the stretching and reaching movements that some clinicians recommend as physiotherapy for PD patients. The user simply has to move their arm within a close enough proximity to one of the 4 ultrasonic sensors which correlate with different movements of the robotic arm, and then the servo motors of the arm will rotate, allowing the arm to be positioned for the user's next move, whether they can pick up or release a chess piece. Ultrasonic sensors operate through transmitting an ultrasonic pulse and receiving its reflection, with the time between these pulses informing the distance between the target and the sensor. Our software pipeline determines proximity from 2 to 500 centimeters across each ultrasonic sensor, employing a threshold of 10 centimeters to signal an active command. We employ a moving average filter across the distance measurements as a means of smoothing. When an action command is triggered, this alters the pulse width modulated signal sent to the servo motor to achieve a certain angular displacement. This rotation enables the robotic arm to move.
The EMG component of the device also serves as a means of physical exercise for people with PD, as the device requires forearm contraction to trigger the opening and closing of the claw, which is attached to the end of the robot arm. This movement allows for the chess piece to be gripped and released. The signal is captured from the forearm by the 3 nodes and sent to amplifier to filter and boost the signal. After the signal enters lab view, the raw signal is filtered by bandpass filter and the moving average filter. The threshold was determined and is used as the trigger of opening and closing of the claw.
The robotic arm is attached to a rail system, which allows it to move laterally along the chessboard through the use of a lever. The user can simply move the lever left and right, and the robot arm will follow. This allows access to all areas of the chessboard task space while minimizing interference with other chess pieces. The lever is connected to a joystick sensor, which in turn is connected to an Arduino microcontroller. Only one axis of the joystick sensor is wired to the system, so the joystick has been physically limited to a single axis. The voltage reading from the potentiometer within the joystick sensor tells the microcontroller its current position. When this voltage exceeds or falls below certain threshold values, the relevant digital signals are sent to the stepper motor. The stepper motor operates at constant speed to improve predictability for patients with reduced fine motor control.
Altogether, we report the integration of multiple signals, proximity detection via ultrasonic sensors, muscle contractions through an EMG sensor, and a lever, to control a multi-servo motor robotic arm mounted on a stepper motor controlled rail system.
Through 3D printing our components for customization, creating software open for calibration and modification, and thorough testing, it is our hope Bobby Fischer can deal with the mechanics of movement so our users don't have to.